Welcome back to our final keynote of the day. My name is Eric Brunvand. I'm a professor in the Kahlert School of Computing. And now that you've given me a mic, I'm also going to say that I'm also the conference chair for the SIGGRAPH conference this year. And I would just like to say if I could get just the reserved seating to come to SIGGRAPH in August in 2023, it would be the best SIGGRAPH ever from a graphics pioneering point of view. The number of graphics pioneers in this audience is astounding. So talk to me. Let's talk about SIGGRAPH in August in Los Angeles. But of course, I'm here to introduce our keynote speaker. It gives me great pleasure to introduce Evans Sutherland. I'm sure I don't have to tell people in this room that he was honored with the Turing Award in 1988. Now, when you're introducing a Turing Award awardee, you're tempted to go look up all their achievements and accolades and spend a lot of time talking about all the wonderful things they've done. I'm not going to do that. For purposes of this celebration, note that Ivan was a professor in the fledgling Department of Computer Science from 1968 till 1974. Also in 1968, he founded, along with Dave Evans, the Evans and Sutherland Computer Company, which was a hugely pioneering company in graphics, both software and hardware. I think many people in this room have at least spent some time at E&S. I know, Jim Clark and Shane was there. I was a student intern there when I was an undergrad, so I have some history at E&S as well. I've known Ivan for a long time. He was a member of my PhD committee at Carnegie Mellon, we'll just say a long time ago. And the thing that I've always found wonderful about Ivan is that when he gives a talk, I know I'm going to learn something interesting. And for this particular talk, I know just enough about single flux quantum devices to know that I need to hear from Ivan about single flux quantum devices. So join me in welcoming Professor Ivan Sutherland.
When I was asked to come to Utah to this occasion, I said, I don't want to say a word about graphics. I haven't done any for 35 years. Not quite true, but very nearly true. But I would like to give a talk about the subject at which I'm now excited, a subject at which very few people even know exists. And the way I got involved is 5 years ago or so. A very clever man named Gary Delp asked me to go to the MIT Lincoln Laboratory on my way back from Heidelberg. Now, the Turing laureates meet in Heidelberg in September typically. They bring 50 or so of the, they bring nearly 100 of the Turing laureates to the meeting, and several hundred students from worldwide. And the idea is that something rubs off from one group to the other. I'm pretty sure that most of what rubs off is from the young people to the old farts. But, that's not the intent, but that's what happens. Anyhow, I went to the Lincoln Laboratory, and I found that they were making these amazing circuits. And I got intrigued, and so I spent the next several years learning things about this technology, reading the papers, working the problems, doing the simulations, trying to figure out what the hell is all this about. It's really weird, but I'd like to talk about it today, and that's the subject of my talk. If you're here to learn about quantum computing, go somewhere else. Now, it's been my great good fortune over the years to have a number of very clever people working with me. At the moment, I'm working with a man named Warren Hunt. Warren Hunt is able to prove mathematically that your floating point arithmetic unit, in fact, does IEEE standard floating point. And he does that in a few minutes on a laptop. If you want to know how he does that, I think I can explain that too. And here are some other people. Marley Ronkin, my life partner and research partner, is here. We have students, a couple in Portland. Gary Delp, I mentioned. Steve Rubin is a man who wrote a program called Electric Open Source, which I think of as Sketchpad grown up. And the Lincoln Laboratory people have been very kind to me. Here's 3 of the people that I meet with regularly. Now, this talk has a few parts. There's an introduction. I'll give you this introduction briefly, and then I'm going to give you a laundry list of reasons I'm excited about SFQ. And then I'm going to give you a laundry list about the unfamiliar challenges that it poses. And then I'm going to talk about the history and future. Now, I believe that the work that we did at Utah worked for 3 reasons. The Harvard Business School came and tried to do a study to see if it could be repeated. And they said, what made it work? And I think there were 3 things. The first was there was a worthy intellectual opponent. That was, how do we do graphics, realistic graphics? There was money. DARPA provided money. And the third thing, which is the most important thing and the hardest thing to get, is leadership. We had Dave Evans. Dave Evans was brought here to the University of Utah, particularly to found a computer science department. And I'd like to mention that the very first Turing Awardee, a man named Alan Perlis, came to visit us when computer science was new at University of Utah, and he looked at the sign over the computer science department office, and it said computer science. And he turned to everybody and said, would you tell me, please, what that is? That's still an important question. Okay, so here we go. 50 years ago or so, there was a semiconductor revolution, which made everybody aware of semiconductors and what they could do. And then there was this idea of Moore's law. We kept getting more and more and more and more switching elements on a chip. And so there was a tremendous economic multiplier when all of these things did all sorts of things, gave us cell phones and communication that we're accustomed to now. But then it appears now that the ability to get more transistors every year is decreasing. Moore's law is coming to an end. And so what's going to happen after that? I fear that the US may lose the enormous economic advantage that we've enjoyed by commanding the semiconductor industry for so many years. Why is that going to happen? Because a lot of people think electronics means semiconductors, means transistors. And memory, they think, means random access memory. The RAMs, the SRAMs and the DRAMs that you're familiar with. And not only engineers think that, but also managers. And public officials think that. Because that's what electronics is today, but it's not the only way to do electronics. So let's look beyond this idea that electronics is semiconductors and transistors, and that random is random access memory, where larger means we're going to go slower because the speed of light, I've come to call it the slowness of light rather than the speed of light, is a fundamental limit which we can't pass. And here's this family of circuits called single flux quantum digital circuits. And they exploit superconductivity to offer a plausible alternative. SFQ circuits are fast, they're very fast. In fact, the fastest counter that's ever been built is built in this technology. Single flux quantum circuits differ from quantum computing, and here's the ways. They're available today. They're general purpose. They're Turing complete. You can do anything with them. They're digital. They're familiar. Quantum computing seems to be available soon. It's applicable to only a few, albeit important tasks, and it's largely analog, and it's very hard to build because it requires super, super, super cold, very near absolute zero. Now, did you know that magnetic flux is quantized? Everybody accepts that electric fields are quantized because there's a single electron. And everybody knows the charge on an electron is ever since Millikan's oil drop experiment, which, by the way, was probably done by some of Millikan's graduate students who don't get the credit. You know, Millikan was famous for taking credit for things. The unit of professional credit is the can, but the practical unit is the millican. Now, Schrodinger's atom shows that electrons, although they're quantized, they occupy space. They have these orbitals that they go through, and so they really are a kind of field in addition to being quantized. So why is it so hard to imagine that magnetic fields might also be quantized? It would be rather surprising to expect they weren't. Everything else seems to be. And by the way, these are all numbers that are known to at least 15 significant figures. Planck's constant, the charge on the electron, the size of the unit of magnetic flux, and there's this funny product that shows that they're all interrelated in a very unique way. Now, here's my laundry list about why this stuff excites me. The first thing you need to know is I hate the wires on integrated circuit chips. The wires on integrated circuits occupy all the area, they cause all the delay, and they cost all the energy. What's to like about a wire? I mean, these are terrible wires. They have resistance and they have capacitance. And so your idea that electricity flows through a wire is wrong. Electricity oozes through a wire. It has to charge up all that capacitance and it has to get through all that resistance. And the result is that the speed of conduction through integrated circuit wires grows with the square of the distance rather than the distance. The delay is the square of the distance. How terrible is that? Now, SFQ circuits use superconducting wires. There isn't any resistance at all, not just very little, but none. Zero is a very important word. You put a zero in a denominator and very strange things happen. You can put a current in a superconductive loop and start it going around, and it'll go around and still be going around months later. Who'd have thunk? Now, I've come to think of the slowness of light because light goes only about 100 microns per picosecond. 100 microns is about the width of 4 human hairs set side by side. And a picosecond is a short time, but that's how far light goes. The speed record of any binary counter ever made was done in SFQ circuits. It ran at 770 gigahertz, fastest in any technology known. The slowness of light matters. You know, Grace Hopper used to go around with a foot-long piece of wire saying, "This is a nanosecond." And you can see her on the web. There's a wonderful web film of Grace Hopper doing that. I urge you to have a look at it. In our laboratory in Portland State, we have 2 rooms. One of them is called the Alan Turing room, and we have some posters up of Alan Turing. And the other is the Grace Hopper room. We have a wonderful picture of Grace Hopper in her admiral's uniform. And we don't have the thing, but we have a picture from our notebook of the original computer bug. It was a moth that flew into one of the relays in the Harvard Mark IV. Now, I went to the MIT Lincoln Laboratory, and there they had a production line that was building integrated circuits using superconductive materials. And here's the cross-section of their process. It's a 9-wiring layer process. It has some vias that take you from one layer to the other. Now, when you have aluminum wires or copper wires, you put a plug in the via to make the via conduct from one layer to the other. They don't do that here. They just cut a hole in the glass. The insulation is always glass, by the way. Maybe you don't know the reason that silicon is used as the basis for transistor circuits is twofold. One, silicon is a superconductor. But the more important reason is that silicon dioxide is glass. It's a tremendously good insulator. And these circuits are also built on silicon wafers, but those are just mechanical substrates at a place that you could lay down glass as an insulator. The silicon does not enter into the game at all. The vias here are just holes in the glass, and then the next layer of niobium. Niobium is the superconducting material that goes down into the hole. Now, I've had the good fortune that the MIT Lincoln Laboratory built the group of people I work with a couple of integrated circuits. The active element, you have to have a nonlinear element to do anything that's going to involve digital stuff. And the active element here is called a Josephson junction. The Josephson junction was predicted. It was not invented. It was predicted by a man named Josephson, who got the Nobel Prize for doing that. And 5 years or so later, somebody actually showed that it did what he said. It's a very strange device, but it's quite simple to make. So here's a piece of a layout of a piece of a chip that will be superconductive. And it just shows that these are the same kinds of things that you make integrated circuits out of. Now, the zero resistance is the big deal. The most important thing is the worst part of semiconductor electronics is the wires. And here the wires are perfect. No resistance. Signals will go through these wires at the speed of light in the dielectric around them, which is glass, so that speed. And by the way, almost every computer operation involves moving data from here to there. That's what computers do most. It costs more energy and more time to get two numbers out of memory and into a floating point multiplier than it takes energy or time to do the floating multiplication. What do computers do? They move data around all the time. Now, these are the very first really digital circuits I've ever seen. Why are they digital? Because flux is quantized, and so you can take a quantum of flux and you can move it around here and there like a bead on an abacus. The other digital circuits are really analog circuits just masquerading. There's some level, and you say above this level we'll call it a 1, below this level we'll call it a 0. What about right at the level? Well, maybe. It's kind of a perhapsatron. A flux quantum either is or it ain't. You cannot make half of a flux quantum. No way. Now, these circuits run at very low energy. They involve only millivolts and only microamps. So the energy is incredibly low. And because of that very low energy, you could pack these things very closely together and still get rid of the heat. The big problem with semiconductors is getting the heat out. A semiconductor chip that size can produce, hundreds of watts. How do you cool that? Very difficult. These guys are so low energy that cooling them is a smaller problem. So you can make computers very small, and because they're small, the speed of light delay doesn't get you. And so they could be fast. Okay, now the single flux quantum circuits are a worthy intellectual challenge. They're worthy in the sense that they have value, because for all the reasons I told you. They're a challenge because they're entirely different from what you know, and so you have to forget things. And my opinion is it's harder to forget what you're taught than to learn new stuff. And that's the value of students. They don't know what can't be done, and so they just go ahead and do it. Okay? I mean, it's amazing what those people do. If you want to know what the future is going to be, ask the people who are going to make it. Okay. So here's the first challenge. This is a pulse technology, not a level technology. You do not send down a superconductive wire a level. I have an electric vehicle with a plug-in. It's a plug-in hybrid, and it has this electric cable that I plug into the back end there to charge it up at night. And the cable it's a big substantial thing, it's that big around and it's long, and I have to move it. Now I have two choices. I can pick the thing up and carry it, which I hate doing, or I can take hold of the end of it and go like that. And that piece of the cable lifts off the ground, and then this piece that's off the ground moves to the other end of the cable, repositioning the cable. I never had to lift the whole thing. That's the secret here. You don't ever change the voltage of the entire wire. You just change a little piece, and that little piece moves at the speed of light down the wire. Well, now that poses a conundrum. We have a pulse like that, and we use it to mean yes. So what do we use to mean no? Well, this is the conundrum that a student who comes into the classroom and there's no professor. How long does he wait before he gives up and goes home? It's the problem that everyone who's waited for his wife has. How long do I wait before I go home? Or every wife who's waited for a husband. The pulses that travel down last only a picosecond or so. Here's some pictures from a simulation of a bunch of those pulses. These are colored, so you see the difference of them. But every logic gate in this technology has to have some memory in it to remember whether or not it got a pulse on that input. So a gate that's going to produce the AND of A and B may get a pulse on A, and then sometime later it'll get a pulse on B. And the pulse on A arrived at one time, and the pulse on B, which is only a picosecond long, arrived at some other time, not the same picosecond. And so it has to remember that it got A, and when it gets B, it has to say, oh, I remember I got A, then I can produce an answer. But wait a minute, when does it produce an answer? And in these gates, you have to tell the gate when to deliver its logical answer. And this is one of the enormous differences. I'll come to that in a minute. Now, everybody thinks that memory is random access memory. The guys at MIT who invented the magnetic core memory spoiled us. They said, we can put these millions of little tiny donuts of ferromagnetic stuff in them, wire them up on X and Y coordinate wires, and then we can select any one and tell what that bit is. And then some guys at Texas Instruments invented the DRAM. They said we can do the same thing using electrostatic storage on chips, but we can get at any bit. And so we've become spoiled. We think that memory is something that allows us to access any part of it equally easily. Wrong. It allows us to access any part of it with equal difficulty because it's somewhere else. This came as a great shock to me when a consultant at Sun said, by the way, you know that the DRAM which is the dynamic RAM that's stored, which we all thought was slower than SRAM, is faster than DRAM, is faster than SRAM. I said, why? He said, because it's smaller. Now, I remember when computers were made with serial memory. They had mercury delay lines. They had pieces of wire that they sent sound down, and then they had a detector at the far end. And you could send all these pulses down this piece of wire, and that was the best memory you could get. Well, it turns out you can make that kind of memory in this technology. Pulses go down these wires. And so you can send pulses down these wires. You could have an integrated circuit just has a long piece of wire in it. And that's pretty good memory. And the density is pretty good too. So it isn't that memory is hard, okay? It's that memory is different. Now there's the unfamiliar electrical behavior. Everybody knows that current follows the path of least resistance. But this is a technology where there isn't any resistance. How's a poor piece of current supposed to know which way to go? The truth of the matter is current's lazy. It goes down the path that uses the least energy. Did you know that horses stop trotting and start to canter? When it's easier to canter, it consumes less energy. I had a wonderful friend at Harvard whose name was Tom McMahon, and he had a treadmill that he had various animals. He took the animals to the treadmill and had measured their metabolic rate and so on. And he said, it's absolutely clear. As soon as it takes less energy to run in a different gait, that's what they do. Even kangaroos. Kangaroos like to hop at a certain speed, and if you ask them to hop at a different speed, they don't like it. Current is lazy. Now the worst part, the hardest part to understand of SFQ is called phase. And what phase is, it's the phase that Schrodinger talks about in Schrodinger's wave equation. It's essentially, you have to think about an electric current as a wave thing rather than as electrons moving. And the wave has peaks and valleys and so on. And the phase of the circuit is how far you are along those peaks and valleys. And I think of that much as this wonderful picture by M.C. Escher, where you see a whole bunch of monks who are climbing the stairs forever and ever and ever and ever and ever and ever and ever. And after they've climbed a while, they're back right where they started. And phase is a potential, just like voltage. Kirchhoff's laws in this technology follow the rules of phase. And everybody knows that when you go around a closed loop, Kirchhoff's laws says you the sum of the voltage drops around that loop is zero, right? Well, not quite true with superconductors and phase. When you go around the loop, the phase is equal to the number of fluxons trapped in the loop. Who'd have thought? So you have to think of phase as sort of how far the monks are from the tower. So we're dealing with a potential, like voltage, which is cyclic rather than monatomic. And that's hard to grok. I just admitted it's hard to grok. Took me a year. Okay, once you get the idea, then you realize the important thing to think about is whether one phase is ahead of another or behind it. You have to think about that because the current is just the phase divided by the inductance. It's the same as the current is the voltage divided by the resistance. It's not hard, it's just different. So I think of a phase as being ahead or behind another phase. Now the thing that we have all familiar with, which is cyclic, is the days of the week. And I ask you, is Wednesday before or after Saturday? Well, it depends, right? Now there's a beautiful thing about that, which is if you have one of these circuits, and think about the phase, and the circuit goes through a phase cycle, when it's gone through 360 degrees of that phase cycle, it's back where it started. So you don't ever have to reset it. Now, one of the circuits that we use is a thing called the Josephson transmission line. It's like a bunch of dominoes. You push one down, it knocks the next one down, knocks the next one down. But these dominoes automatically set themselves back up again. Wouldn't I love to have had that when I was a kid? Okay, let's talk about how it happened and where it's going. Now, there was a research group, much like the research group here, and it had a wonderful leader, quite like David Evans. I've had the privilege of meeting the man. I quite like him. But the man was named K.K. Likarev, and he wasn't in Utah, he was in Moscow. And that's about when we were here. And in those days, Moscow was a lot farther from Salt Lake City. Well, it's still pretty far. And Likarev and his students had a group much like the group that did graphics here. And those students now populate the superconducting world. Okay? Some brilliant US person bought them airplane tickets to come to the USA. And they came, a whole bunch of them. And they're now distributed around. There's a part of the brain drain. Thank heavens this happened. They're here, or they're contributing. But wait a minute, they're all reaching retirement age, so that's another issue. Now, where did Likarev get his support? Well, he was called into the top level of the USSR's political group and asked to give a presentation, which he did, and they gave him a whole bunch of money, research money. And I think it was their intent to try and create another Sputnik, because this was right when IBM was making a big splash about its investing in superconducting. And he commissioned them to try and outdo IBM. And of course, nobody noticed, because then the USSR collapsed and his funding ran out. But I think it did outdo IBM. Why? Because IBM tried very, very hard to preserve level logic. They said, we want all of the kind of gates that we know and love to still work. And Likarev didn't have any background like that. He said, let's look at what the technology can do, and let's do computing the way it says we must do it to make advantage of its capabilities and limitations. And I think that Likarev succeeded where IBM failed. By the way, these guys are now reaching retirement age. Now, one of them is a man named Topolgo, who is the guy who builds these circuits at the MIT Lincoln Laboratory. He's the head of their niobium integrated circuit stuff, using used leftover integrated circuit manufacturing stuff, and he builds these circuits. And boy, I heard him complain one time. He said, there are these wafer probers that I could get that will work at superconducting temperatures, and boy, I wish I could get one, but my budget won't afford the $1.5 million price tag. And then he said, 4 of these machines recently shipped to China. Oops. I mean, I think we're in a serious problem that we may well risk the next generation of electronics to our economic competitors. How do we avoid that? I think what we have to do is invest nationally in SFQ research and training. Don't forget the training. Who's going to do this stuff? The students that aren't yet in the graduate schools teaching this stuff. Now, I had a front row seat at the at the birth of the semiconductor revolution. Carver Mead was my colleague at Caltech, and Lynn Conway, who was the other author of that famous book, worked for my older brother. She was in his group at Xerox PARC. That's how they met. The book that they wrote, is called, I forget, it's called Mead and Conway. It has some title, but nobody cares. And it's dedicated to W.R. Sutherland. Who the hell is that? That's my late older brother. He paid for it. He hired Mead as a consultant to come to Xerox PARC and just stir up the troops and do whatever, and this book resulted. And then he paid for an initial set of chips to be built by students to test their ideas. Now there's some important differences between the SFQ digital technology and the CMOS technology. In the CMOS technology, a transistor sends a level down a wire, a 1 or a 0, and in its good time, when the receiver is ready for that value, the receiver takes the initiative and captures the value. But in a pulse technology, you haven't that luxury. Okay? It's an entirely different deal. The sender is going to send the pulse whatever the sender is told to. The receiver had better be ready to receive it, or it's got to be gone. It's only a picosecond long. And I think of this as a little the difference between the courtesy that one gender can extend to the other. My father was born in 1897. I point out to you that Victoria was the Queen of England at that time. And he was a proper Victorian. And he said, a gentleman always extends his hand to a lady. And if she wishes, she could put her hand in his. Okay? But this technology ain't like that. It's going to grab, it's going to say, here's the information, better take it now. That's a total difference. And it makes a huge difference to all the software that decides what these things do. I think that academia is going to provide the new software that's going to meet those constraints. I remind you that SPICE, which is probably the biggest tool that's used in the simulation of transistor circuits, came out of academia. I believe that federal support is going to become available. The NSF recently gave a grant to USC, major grant, to teach this technology. I think that's terrific, but it's a drop in the bucket. We need thousands of engineers who understand this stuff. They aren't all going to come out of one university. And are you going to trust USC to be the only place in the country that teaches this stuff? I don't think so. I think we need a number of places. Why not University of Utah? I mean, we've done it before. We could do it again. Okay? How do we do that? How do we do that? I think given those thousands of engineers, we will field single flux quantum digital systems that will provide us enormous amounts of computing capability, and it can be small. My vision is the supercomputer in a shoebox. A supercomputer today is at least as big as this room. How long does it take light to get from there to there? Long time. That slows down the operations of the supercomputer. But I think that these things are so low power that getting the heat out of a shoebox is possible. Now, admittedly, once you got the heat out, the heat came out at 4 degrees Kelvin. That's really cold, guys. So now we've got an immense refrigeration problem. We got to take all that heat, get it out of there, and pump it up to room temperature, or preferably to outside where we have some kind of cooling tower. That's going to cost a lot of energy. But think of that cost as the cost of making the thing fast, because it's small. It's not the cost of making it work, it's the cost of making it fast. You could pay any amount of cost to make it fast. That's giving you a huge advantage. I've come to the end of this discussion.
Questions?
Thank you. You mentioned that this lab made 2 chips for your group. Did I understand that correctly?
Yes,
And one of them worked and one of them is still being tested.
that's right.
What does the one that worked do, and what is the other one that's being tested
The
hope
one
to do?
that barely worked, and it, mind you, it barely showed signs of life, was merely a level converter to be able to take these tiny little pulses and see them in the outside world. That worked just well enough to know that, well, it's not hopeless. The second one is a thing called a TAP controller, a test access port controller. An important part of using JTAG, which is the IEEE standard way of testing chips, is a thing called a TAP controller, test access port controller. JTAG uses only 5 wires. You run 5 wires onto the chip. Why do we do that? Because wires going onto a chip are very expensive. They occupy a lot of area on the chip, which we'd rather use for productive means. So JTAG is an IEEE standard, 20 years or more old, which tells you how to do that with 5 wires. JTAG requires an on-chip controller, which is just a state machine, which interprets signals on those 5 wires to control a whole bunch of scan chains, which go and collect data from all over the chip and deliver it serially down one wire, and take data serially up another wire and distribute it out to all over the chip. When I went to the Lincoln Laboratory, I realized that these chips are very cold. So any wire that you put in takes signals in or signals out. Oops, it also takes heat in. Oops, we don't like that. So I said, of course you use JTAG to test this, don't you? What's JTAG?
Thank you.
So that, your answer, I think, may have gotten part of mine. If I have this shoebox full of magical gunk that does amazing things that's running in, let's say, 4 Kelvin or some such, and I want to say, oops, it's not working right, I need to inform my, let's say, future versions of Shoebox Plus, is your vision that it will be JTAG?
I believe these things are perfectly testable. I mean, you put a JTAG controller on, we know how to build scan chains. They're not even very hard. In fact, everybody who tests superconducting chips now does it with serial to parallel conversion. They do that because that's the only way to get few enough wires. They don't use the JTAG standard because it's not become common. But it will.
Okay, so then the real problem comes down to heat in that you have to work on?
The real problem comes down to people who know what they're doing.
Fair enough.
I have to tell you, I'm not a good RSFQ designer. I haven't made nearly enough mistakes to know what not to do. And engineering is a process of avoiding mistakes. And you have to make the mistakes below you know they're mistakes to avoid. Balconies have to collapse. Turbines on ships have to blow turbine blades in mid-sea. How embarrassing, okay? Before you learn what you have to do.
So the question I've got is, we were extremely fortunate in that ARPA, because of the existential crisis, was willing to fund a number of things. What's the impediment for them responding to this? What gets in the way of providing the kind of funding that's necessary to run this?
I got it. The question is, what's in the way of federal funding? I think the answer is not enough people know that this technology even exists. There was a study done by the NSA for the future needs of their computing. They use quite a lot of computing, I might mention to you. And this is a 2005 study. I have a copy of it. And it says, this is a technology that we should explore. Now, Likarev was on the committee that wrote that document. There was a later study done by the Jasons which said, forget it. This technology will never achieve anything because the cost of getting the heat out of these circuits is so great that they'll never give you a power advantage. Power advantage, smower advantage. I don't care about a power advantage. I just want speed. How do you get speed? You make it small. The power advantage is irrelevant. But the Jason study didn't say anything about the wires. They said the transistors are just as good. They switched with just as little energy as these things, which is true. But every transistor drives at least one wire. And it's the wires that consume all the energy, not the transistors. And so I think they missed the bet. And I think that has put a damper on the enthusiasm of people who control money for this technology. And then quantum computing came along. It's the answer to everybody's prayer. It can do everything. I think it's going to be a long time before a quantum computer computes a payroll. I think it's a long time before it does a large data search. I think there's many things that we're going to wait for. And a lot of money got channeled into quantum computing. And as a result of that, that's not all bad, because as a result of that, the ability of people to refrigerate got better. And a lot of other things developed that were good. Now, I went to the supercomputing conference in Hawaii some time ago, and I discovered in Hawaii that liquid nitrogen was very expensive in Hawaii. Now, I'm sure in the medical department up here, they have little styrofoam cups of liquid nitrogen. They dip their Q-tips in it. They touch your spots to try to freeze them out. Many of us have had that experience. Liquid nitrogen's cheaper than beer. Do you know why? Because it's a byproduct of making steel. The way you make steel today is you take a tub of molten iron, and you take a pipe and you stick the pipe in it. The pipe gradually melts away, but who cares? You blow oxygen down through the pipe. The oxygen bubbles in the molten iron and burns out the carbon. And then you get stuff pure enough that you could add the impurities that you need, and you get steel. Liquid nitrogen is a byproduct of making steel. There's no steel industry on Hawaii, and so liquid nitrogen is very expensive.
What about the high temperature superconductors, the cupric oxide compound?
That's a wonderful question. That's a wonderful question. It's one of the really good questions. High temperature superconductors have been invented. They run at liquid nitrogen temperatures instead of liquid helium temperature. But the thermal noise energy is quite high. The reason you want this stuff cold is so that little tiny signals can still sit over the noise. And even at liquid nitrogen temperature, there's enough thermal noise that you'd have to have signals 100 or 1,000 times bigger. One of Likarev's papers talking about this says it came as a great disappointment to him when the high temperature superconductors were invented. And he said, oh, darn, we can't use those. Pity.
Now there's a company in Holland which makes cheap refrigeration systems with Stirling machines, and that might be a possible solution because they can. The first time I learned about this, it was originally the big Philips company, big electric Philips company who invented these machines. And the first time I saw it is they were demonstrating how you could float a magnet over superconducting lead with their machines. So those machines are quite efficient. And so that's an advantage that some people might learn about.
Yeah, I think it's interesting that refrigerators that will refrigerate to these temperatures are quite available. They're not very big, they're not very expensive. So, you know, this stuff is within reach of, you know, reasonable places to do.
Ivan, I don't want to use the four-letter word wire, but have you...
Say it again?
I don't want to use the four-letter word wire, but have you, your associates, looked at using two-wire encoding as opposed to the presence and absence of a pulse?
Of course. The reason I got into this is that Gary Delp knew that I was interested in asynchronous stuff, thanks to Chuck Seitz. Chuck Seitz is the guy to blame for getting me into asynchrony, and a number of other things that he got me into. But of course, and that's why he suggested that I stop at the Lincoln Laboratory on the way back from Heidelberg. That's why he sent me there. And I've talked to various people about this. I went and gave a talk at Hypers, and there's a man named Oleg Makhadov. Does that name sound a little Russian? Okay, and I gave my pitch about, you know, asynchrony and so on. He says, yeah, we thought of that. In fact, he said, we'd followed all of your papers. They knew that asynchrony was important in Russia long ago. They knew about the Seitz arbiter. And we had a violent agreement about how important asynchrony was. And of course, you can do all the tricks. You can use the two-wire trick. You can use the common one is, you know, the bundled data. I think you're responsible for the word bundled data. You send a whole bunch of signals, pulses down this wire, and then there's a separate wire which says, okay, guys, the bell is wrong. If you ain't got a 1, it ain't going to come. Think it's a 0. It's as simple as that. And there are all those techniques that are applicable here, and they're important because the signals go at the slowness of light. And so where you are on the chip matters. How you arrange things so that the computation flows in a uniform way, and the things that have to be done first are done nearby, and the things that can wait get done further away. I mean, there are hundreds of things to explore here. It's amazing. This is a field where, you know, anything you do is going to be almost brand new. Well, not quite, because there's been other people who've, you know, done some pioneering. You know, we wouldn't be able to do any of this if we didn't have Joseph's injunctions. Okay? We wouldn't be able to do any of this if we didn't know that superconductivity exists. You know, the IBM guys said, we're going to switch the superconductivity on and off, which you can do. But it turns out switching superconductivity off is easy, because superconductivity is the result of electrons kind of forming a crystal in the wire and then moving en masse, and so none of them can see the atoms that are in the way. And that's how you get superconductivity, by having a very regular flow of current. Getting rid of superconductivity is easy. You just create chaos. Superconductivity is gone, resistance is back. Doesn't take any time at all. Getting it back is hard and slow.
So it would seem that there are some areas closer to that temperature that the government does have an interest in, space, perhaps that may be an entree to funding.
Oh, you bet, absolutely. I mean, the recent telescope images that we've seen from the James Webb telescope are all collected at superconductivity, at very low temperatures, because they have to. They're thermal signals. They're collected from infrared. And the best magnetometers that are known are made with Josephson junctions. You make a thing called a SQUID, which is a superconductive quantum interference device, SQUID. It consists of two Josephson junctions in a loop, and if there's magnetic flux going through the loop, they behave differently than if there isn't. Makes a very sensitive magnetometer. And so I can imagine making magnetometers which could be held close to a person and sense the magnetic fields produced from nerve actions. I mean, there's many things that can be done, but we just have to do them. And who's going to do them? It's the graduate students. It's the people we saw in the video, the young assistant professors, the young people who have ideas, who encourage other young people to think up new things. I'm here saying, look, there's a field here, and I've got excited about it because it seems right to me. It has the feel to me of something which has legs. But I'm not going to live that long, guys. I'm 84 now, okay? And thank God I have something exciting to work on. Otherwise, I'd have gone crazy during COVID. I mean, COVID came down, I had to stay home. All I could do was simulate circuits, read papers, try and understand this stuff. So, that's why I'm here, thanks to COVID, right? My mother used to say, it's a very ill wind that doesn't blow somebody some good.
I have a question. You mentioned that...
I'm not hearing this at all.
Okay.
I'm right here.
Yeah, I'll tell you. He hadn't said anything yet.
You mentioned that China purchased for, I don't remember what they were called, to do this type of research. How difficult is it to actually create one of these chips? Earlier in the NVIDIA presentation, they showed an EUV machine that I think he said it was $500 million, and I believe Trump and Biden are both trying to make sure China doesn't get that technology. Is this type of technology something that China could actually create on their own?
I think absolutely. Making Josephson junctions is quite easy. Okay, I'll tell you how to do it. You lay down a layer of niobium, then you coat it with a very thin layer of aluminum. Now, it turns out a thin layer of aluminum next to a superconductive niobium layer is also superconductive. Don't ask me why, I'm not a physicist. Then you oxidize the aluminum. You expose it to oxygen at a certain temperature, a certain pressure, for a certain length of time, and you get a very thin layer of aluminum oxide on the surface. Aluminum oxide is a very tough insulator, and this layer of aluminum oxide is a few molecules thick. Then you lay down another layer of niobium. Behold, a Josephson junction. And the Josephson junction is an amazing thing. When a Josephson junction carries less current than what's called its critical current, it is a superconductor. No resistance. As the current increases and increases and increases and increases, there comes a point where the Josephson junction says, nope, no more. That's called its critical current. And suddenly it becomes resistive. The equation for that is that the current through the Josephson junction is proportional to the sine of the phase drop across it. The SIN, the trigonometric function of the sine. And that's not an approximation. That's what the quantum physics tells you it must be. And so the ability to apply algebra to these circuits is wide open field. You know, the state of the art in optimizing these circuits is to simulate them and then change the parameters a little bit and simulate again, then change the parameters and simulate again and so on until it fails. And then you change the parameters the other way until it fails. And then you take the midpoint of the two and say, I'll run there. This is like, how do you find the furthest distance from the edge of a funny shaped swimming pool? I want to get in the middle the failure is like a SPU diagram. It's all the places that they fail. A fighter pilot has many ways that it can fail. The wings can fall off, the jet can burn out, you know, the pilot can black out, anything can happen. That's called the envelope. If you look at a multi-dimensional plot of all the places where it'll fly okay and all the places where it won't, that's the envelope. And what ace fighter pilots like to do is fly really close to the edge of the envelope. And what you want to do for optimizing the circuits is get as far away from the envelope as you possibly can, because then the manufacturing defects won't screw you up. And the state of the art of doing that is just go out until you touch the envelope and then go out the other way and then take someplace in between, right? I don't think that's any good. We got to be able to do better than that algebraically. The circuits are all subject to algebraic equations. We now have computer help doing algebra. Why can't we do this algebra and just get the right answer? I mean, I learned long ago, arithmetic is how you get one answer. Algebra is how you get all the answers. Calculus is how you get the best answer.
Has there been any research on using time delays as the way of encoding signals?
Research on time delay.
I'm sorry?
Can you repeat?
Temporal distance between the pulses encodes on the human neuron in a similar kind of pulse-based transmission line. Is there any work that's been done with this physical interface in order to be able to use that as the encoding rather than the current ones that are being used?
Did you get that? Did you get that?
We are not able to understand.
You have to, if you could ask the question like in a sentence at a time, then I can repeat it. It's just going too fast.
The human neuron encodes time delay pulses through time delays rather than on a kind of digital interface.
He's talking about the human neuron.
Yeah, the question, I heard the question. What about using the time delay between pulses?
Correct.
Right. This is a terrific idea. There's at least one group that's exploring it. I think it's a wonderful idea. Let me put it in a simple way to say. Supposing I would like to send some information, and all I want to do is use the telephone but not get charged for the call. Okay? So I agree, I'll call you at some time. You'll notice what the time is, but you won't answer. The phone will ring, but you won't answer. And then I'll call you a number of minutes or hours or something later and do the same thing again, and the information I'm going to convey to you is how long between the two phone calls. What a fabulous idea.
Isn't that Morse code?
With two pulses, I can transmit an arbitrary amount of information, which is controlled only by how accurately I can measure the time in between them. So that's a great idea. Let's do it. Will somebody at the University of Utah build something like that? There are other people who are trying. There's a whole algebra of how to deal with it and so
on. You mentioned a lot how the pulse essentially travels with no resistance, like zero, not just a little bit, but zero. How is that true? You know, it feels like we're getting a free lunch or whatever with, like it's just going to go forever, like an object in space or whatever else. How do you know it's actually zero and not just incredibly small, and over what distance is that true?
Well, I don't know about that. I know that there have been currents put in superconducting loops which have lasted for months. So I think the evidence is pretty good. Now, there's a lot of questions about pulses in wires. I mean, all the wires that we have on superconductive chips so far always have right-angle corners. And would it be better to have curved corners? Would it be better that the wire went along and behaved more like a freeway or a railroad track rather than a city intersection? I don't know. I don't know if the experiments have ever been done. But that's one of the experiments I'd like to see done. You know, maybe if we make a serpentine kind of path for a memory pulse, maybe that can give us more wire in a smaller space in order to get more bits stored. But you know, I don't know all these things. I just know there's a worthy intellectual opponent here waiting to be engaged. And somebody is going to engage it, and we're going to get benefit out of that engagement. And I say to the United States, let's get the hell on with it. And the secret to making that happen is education. We need 1,000 trained engineers in this field. 1,000 trained engineers in transistor electronics gave us the electronic revolution. I think we can get a similar benefit out of this, and if we fail to do that, one of our international competitors is going to. Okay? We could lose big. I think I've done all that kind of do. Let's go do something else.
I was gonna, get one more question. I'll just say, that was really great. So that concludes our program for today, and hope to see you all back here tomorrow morning at 10 a.m. for the IEEE Milestone event. Thank you all for coming, and have a good evening. See you tomorrow.
Yay, Mary.